Okay, I think it's time to start our next session. Welcome, ladies and gentlemen, to our session about quality of service. Quality of service is certainly, since some years, a hot topic of discussion of different concepts. Especially this is true in the wide area networking, where on the other hand in practice bandwidth overprovisioning solves the real problems of quality of service. So the whole area of quality of service is certainly very interesting, but also very critical topic for discussion and for reality. But apart from the wide area networking, there are also other views and other needs for quality of service. So we have in our lesson 3 talks about 3 different aspects to deal with quality of service requirements. The first talk will present quality of service experiences in the, let's say, classical environment of the wide area networking. The second talk will deal with quality of service requirements from the application point of view, in this case from the web point of view. And the third talk will present a concept for quality of service in the campus net environment. So we will cover not only, let's say, the classical area, the wide area networking for quality of service. Okay, let's come to the first talk about the usage, about the experiences of quality of service in the Internet too. The talk is presented by Ben Teitelbaum. He is with UCATE, that is the US Association of Research Institutions and Universities. He is there since several years and deals since that time with the establishment of the QBone and the creation of QoS environments, and he will give us an overview about what has happened and about what they want to do in the near future. Ben.
Thank you, Peter. So as Peter said, this is the classical QoS talk. So when we talk about Internet to QoS, we are mostly talking about what happens on the wire from NIC to NIC. So what is our goal here? I like this quote a lot. I've put it up on our website. It is in no way an endorsement of the Crusades or the behavior of the Crusaders as they pass through this area, but the holy grail of computer networking is to design a network that has the flexibility and low cost of the Internet, yet offers the end-to-end quality of service of the telephone network. However, we live in the real world, and the environment that we live in is one where bandwidth is increasing very rapidly, even faster than Moore's law. This is a nice quote from George Gilder that sort of sums up the environment. And this attitude that the companies or the applications that exploit bandwidth recklessly will win. And this is in some ways sort of our attitude in Internet too. We've strived to provide a very high performance, best effort environment for advanced applications to flourish in, and in many ways that does enable advanced applications. But we do QoS nonetheless to enable those applications which have very, very stringent real-time requirements, and as a kind of safety belt approach in case we have a success catastrophe and the relationship between bandwidth supply and demand changes radically. So this is kind of a story of how we charged down a very direct road towards this holy grail of doing virtual circuits, interdomain, end-to-end virtual circuits over the Internet, and thought that we understood understood how to do this, and in fact, we still think we kind of understand how to do it, but it's from an architectural point of view. But the real-world issues of deployment have burned us somewhat, and we're now looking for sort of a more pragmatic approach where we can reap some value as we go down what is looking to be a longer road towards the Holy Grail than we imagined. So that's kind of the summary of my talk. So a brief history. Around late 1997, we began to look at what are these advanced applications, what are likely their needs. We held workshops. We asked these folks what they want. A lot of folks said, well, what can you give us? And there was a kind of a give and take there. And it turned out, there are a spectrum of needs, and some of the best applications out there learn to be adaptive. But even some of the adaptive ones need floors, performance floors to function. But at any rate, there exists a critical set of applications that have hard real-time needs. These are interactive control applications for controlling remote scientific instruments, teleimmersion, some high-performance audio stuff, computer scientists who want to want the flexibility of sort of what was formerly achievable with ATM. They want to build overlay networks to try new networking protocols and so on, and have reliable performance between on this overlay network. So at the same time, there was emerging work in the IETF and thinking of Ben Jacobson and Dave Clark about how to build very, very scalable internet services based on scalable primitives which you would put in the routers. And this was a sort of bottom-up diff-serve revolution, if you will, that started with these building blocks. And we said, okay, we think we know how to do this. We think we know how to take priority queues, shapers, and leaky bucket policers and put together an end-to-end service that looks a lot like a virtual wire. And it's conceptually not hard. So we chartered the Cubone initiative to build upon the standardization work that was going on in the IETF, define some services, and define an interdomain testbed architecture where we could deploy these and debug them. And that is more or less what we have done. We did a lot of architectural work, and that sort of quieted down while folks went off to try to implement things. We're now back doing some more architectural work, and the QPS is the premium service, and more recently we're working on a separate service which I'll conclude with, called QBSS. So just real briefly, the premium service, the virtual wire-like service is built on the expedited forwarding per hop behavior, something morally equivalent to a priority queue at every hop along your path. You mark the packets, indicating that they get access to this queue, and then you achieve a certain scalability by keeping the core routers very dumb and simple. They just trust the markings, and you police very carefully at the edge of your network and at all trust boundaries the aggregate of EF traffic that's allowed to cross that boundary or be injected into your network, and you can build out of this a service that looks sort of like a classical Ben Jacobson vision of a virtual lease line. So the architecture has three parts. One is the service specification. The second part is a reservation setup protocol, which for now is manual. We sort of take the view that, if we can't, why do we need an automated booking system if we can't build an airline yet? So we'll do long-lived manual reservations. But at the same time, we're preparing for success, and we have done quite a lot of thinking and architectural work on a simple interdomain signaling protocol for setting up these reservations. And this work is actually chaired by Phil Comento and is ongoing. You can check our website. The third part is an integrated measurement architecture to collect a uniform set of QoS metrics at the QoS peerings and disseminate them in a uniform way so that we can understand what's going on, provide data for researchers, debug the situation, and so on. So this is the 30,000 kilofoot view. I think that's a different story. The big picture here is to provide definitions and specifications of what happens at interdomain interfaces. So what are the services, the edge-to-edge services across each of these puffy clouds? How do you signal for them cloud to cloud? And how do you measure and audit them at those interfaces? So that's what the architecture specifies. And the idea is, well, how do you take a bunch of edge-to-edge services and concatenate them to form a meaningful end-to-end assurance? And if you're a network operator, your view of how you fit into this architecture is, well, you need to think in terms of how do I provision a virtual trunk from edge to edge of my network, from ingress interface to egress interface of my domain. So that's a pretty high-level view. So, as I mentioned, we are kind of revisiting the architecture, so I want to give you a little bit of a taste of some of the questions we're looking at. It's not a radical revision. There's a design team which is spun up and quite active for the last 3 months or so. We are collaborating very actively with the TFNGN Premium IP group. We're working to clarify the premium service assurance and have a unified service specification between the NGN work and the Internet to Qbone. There are some known bugs in the measurement architecture which we're fixing. And we're really clarifying the implications for operators as to what the SLAs really look like between the clouds. And one of the big issues is really how to balance this sort of service ideal with a very pragmatic need for incremental deployment. So that may have implications in terms of an interim architecture. Other questions are whether to offer a delay assurance. The service specification as it currently is now offers only a loss bound and a jitter bound. Another big issue is in order to do the kinds of classification you need to do to police these virtual trunks, you need to know as traffic enters an input interface to your cloud where it is leaving your network. So you need a hook to routing information in order to do the classification to apply an aggregate to a leaky bucket profile. So we want to clarify exactly what kinds of hooks are needed to routing to achieve that. And there are some interesting questions. I mean, if you look at this sort of picture, little piece of the bigger picture, you've got these, if each cloud is thinking in terms of virtual trunks, then Gigapop B then has these two policers configured on its interface between its boundary peering with the backbone. And in fact, if triangles represent shapers and circles represent policers, this is not going to work. And in fact, what you really need is, does this work? I hear churn. Okay, what you really need is a shaper in front of each policer. And this has interesting, we need to look hard at whether this scales. But we think this is a reasonable model that does scale. Notice that you need as many shapers as your peers have egresses. So it's a lot of shapers. But if you sort of go through the exercise of trying to build a fault-tolerant design where you say, well, what if there's somebody malevolently trying to steal your QoS? You really need this, either malevolently or through incompetence, say a campus which is not policing its users on a /32/32 basis and allowing some host to fire off EF traffic that is off going to an illegal destination. So you need this kind of resolution of policing in order to achieve some amount of fault tolerance, and therefore you need this number of shapers. So there's some interesting questions we're looking at as we revise the architecture, and we hope to make the architecture more informative for implementers. So there's a certain amount of good news here. With enough elbow grease, you can build an end-to-end service. Just sort of building blocks are increasingly available in modern routers. Windows and various versions of Unix can do RSVP signaling. There have been numerous diff-serve test beds, trials. We nucleus of the Q-bone, we have a pale approximation of the architecture implemented in the Abilene backbone, and we peer with another sort of pale approximation of the architecture implemented in a piece of the Energy Sciences Network in the U.S. And we kind of have a nucleus of the Q-bone, and we can do this. We demonstrated an end-to-end premium service at Supercomputing 2000 last November. I'm not going to go through this in incredible detail, but basically, you see a number of domains here represented by boxes. There were two QoS-enabled paths from the West Coast, one from between Stanford and the show floor, which was in Dallas, and from Lawrence Berkeley National Labs through a different path, also to the show floor. Every cloud there had priority queuing at every hop, with the exception of Calren, which was just plain old over-provisioned. And at those lightning bolts, there was congestion induced between these pairs of 7500s in the booth at Stanford and across our peering with the ESNet DOE science grid. The lightning bolt actually on the OC48 link up from SciNet is a little bit bogus. We were hoping that some of the challenge applications were actually going to congest that link, but that didn't happen, and we were not capable of congesting that link. But we were prepared for it there. Anyway, high performance, multi-channel, CD quality audio. Nice demonstration of what happens to an application like that with and without QoS. This worked. In a sense, it's kind of a one-off demo. There's not a lot of policing here. We're not dealing with a large number of aggregate reservations, so you could criticize this on a number of grounds, but it demonstrated a certain amount of success, and that the routers can do the necessary queuing to achieve a circuit-like service. In order to just kind of motivate and catalyze deployment, we decided to eat our own dog food and implement the architecture in the Abilene backbone. And I've been working on this quite concertedly for about a year or so. The Abilene backbone is an OC48 POS core with POS and ATM connections ranging from basically OC3 up to OC48. And the goal here is to make the Abilene Premium Service kind of a reference implementation of the Q-bone. We've got 7 participants, and right now we basically offer them a policing service. They can have the experience of sitting behind a leaky bucket policer that's giving them an EF profile. We're going to be moving pretty soon to turning on the priority queuing, but I'll tell you why in a second. We've got it off. So our deployment experience here, the forwarding piece, we're using Cisco's modified deficit round robin. In summary, it works. The policing, we're using committed access rate. In summary, mixed. I'll give you more details in a second. We did an early field trial with Cisco on some mpls diff-serve aware traffic engineering stuff. That worked in the lab. Shaping we have not yet done, and measurement is spotty but improving. So MDRR is basically a sort of a scalable implementation of a round robin. There's a modified version of it that's in Cisco GSRs, has a special queue that can be configured as a strict priority queue. We have enabled that in the core of Abilene. We did so for the supercomputing demo. It's off now, but we're looking to turn it on again. CAR is the feature that gives you the ability to meter your traffic based on a number of possible matching criteria, including interface, diff-serve code point, or an ACL. And depending on the metering result, take different actions. And so the action we want, of course, is to configure a very shallow token bucket and drop the exceeding traffic and pass the conforming traffic. For the most part, CAR is exactly what the diff-serve doctor ordered. However, there are some limitations on our current gear. Namely, it's implemented in software on the engine 0 zero line cards. So there's a bit of a packet performance cost on some engine zero line cards, up to about 30%. There are constraints on the minimum token bucket depth. This relates to timing resolutions on those cards and how that feeds into the accuracy of the token bucket simulation implementation. And lastly, it's difficult to do this sort of virtual trunk classification. We want University of Washington has 1 megabit to MIT and 10 megabits to Georgia Tech, and we want to police it with 2 policers and know where the traffic is going. Instead, what we're currently stuck with is this sort of Firehose model with a single token bucket at the ingress, and you need a piece of gunk called QoS policy propagation via BGP, which is, I believe, not currently supported on the GSR, although it is rumored to work. So we're working with Cisco to test that out. As I mentioned, we did a field trial of diff-serve traffic engineering stuff. Maybe I ought to take a time check. How far? How much time do I have left? Peter? How much time do I have left? Okay. I will gloss over this then. So the basic idea here is to use mpls as a provisioning tool to do a constraint-based LSP setup and manage your bandwidth pools this way. So this is obviously something that would sort of sit behind a bandwidth broker or some sort of admissions control regime. The draft there from Francois Lefauché is quoted. And as I mentioned, we tested this in the lab, and it basically worked as advertised, although it took us a little while to understand exactly what was advertised. It does provide resource accounting and constraint-based LSP setup. It does not provide upcalls on fast reroute constraint failures so that you would know to sort of tear down a reservation interdomain. It doesn't provide delay constraints that would feed into the LSP setup. It doesn't give you any hooks for this kind of virtual trunk classification that we need, that we're interested in doing, and it doesn't give you any extra mechanisms to protect priority queues. So our big problem now actually really relates to the car limitations, and that is that it relates to the car limitations and our network architecture. So we have a combination of E0 edge cards, which take performance hits if you turn car on, and in some cases engine 2 cards, which are not intended as edge cards facing connectors, and those don't have car at all on them. So we have a serious sort of denial of QoS problem that is preventing us from turning on the priority queuing in the core, particularly since we have some OC48 connectors who could, say, just induce complete starvation across the backbone if we were to turn the priority queuing on and someone were to do something malevolent there. So we have a plan for how to crisp the edge so that we can turn the priority queuing back on. The short-term plan, which I am hopeful will be implemented within the next 4 to 6 weeks, is to do we have actually a very nicely evolving set of NetFlow collection infrastructure, and basically stochastically detect illegal traffic by looking at NetFlow data, and just send non-participating connectors who are injecting EF traffic, just send them nasty grams when they are offending. This is not going to work in the commercial internet, but this might work for us. Our connectors are more or less our friends and are all part of the Internet 2 partnership. So we are going to try that. In the longer term, we will we'll be doing a combination of sort of medium term will be in the medium term we'll be upgrading everyone to new generation of edge cards, which has line speed policing features, and then we should be able to police everywhere. Not listed on this slide, we're kind of looking at the post-GSR Abilene, and we're making very robust line speed edge functionality an important criteria criteria in that design exercise. But the bad news here is that demand is low. It's complicated to do this. It takes a lot of elbow grease, which most campus IT shops can't spare. But most dauntingly, doing this kind of virtual circuits over the internet requires that you upgrade the world. I mean, you've got to turn priority queuing on everywhere. You've got to turn policing on at all of your ingress interfaces, and that could be a lot. So we started looking at ways that we could reap some benefit as we progress. I mean, we're continuing this architectural work. We're continuing to think about how to do this in an incremental way, if possible. But we're looking at some much lighter weight ways to get some benefit out of the functionality that is there. So this is the idea behind the QBSS, which is the Cubone scavenger service. And the idea is, rather than providing better service for special privileged applications and users, we'll provide worse service for anyone who wants it. So the idea here is not as crazy as it might seem. So the user voluntarily marks their packets for potentially downgraded treatment. So if you're a Unix geek, think of this as analogous to doing a Unix nice with a positive value for a Unix process. So it's a hint to the network that it's okay to downgrade the treatment for that packet. Scavenger traffic may be downgraded. So think of this, and then the idea is that that the networks just forward this code point which has global significance, and if there's a congestion point, somebody could look at the traffic there and push the scavenger traffic down to a bottom feeding queue. So think of it architecturally as a sort of completely parallel best effort network that's just thinner, but can still expand to full capacity in the absence of congestion from best effort traffic. And the goal is to kind of preserve this wonderful thing that we know and love called the uncongested best efforts internet, which works for 99.9% of all applications. So I can hear you ask, why would anyone be so crazy as to mark their traffic for worse service? Well, let me try to motivate this. All traffic is not equal. This we know. There's really a mixture of applications there. Some are critical, others are non-critical. Some are tolerant of small amounts of loss and jitter, others are not. You yourself may be responsible for generating some traffic that sits on different parts of this spectrum, and it is in your interest to identify that non-critical traffic which could be degraded in order to get your critical traffic through. So imagine that you are running a very high-performance TCP, you're congesting some point several domains away from you, but you're also trying to run a video conference through that same bottleneck. It's in your interest to let the TCP suffer a little. Another motivation is the queuing is there in the routers. Let's really use it and get some experience with it. Most folks in Internet 2 do not have any kind of differential queuing turned on in their routers, even though it's there. Another motivation is, well, utilization is low. This is a good thing. Most applications work. Most interactive applications here work. But what a waste. What wonderful things could we do if we weren't shy about filling the pipes all the time? What kinds of new applications might emerge? Other motivations. Yes, Virginia, congestion does exist and will always exist at certain places. We have a thing called the Internet 2 End-to-End Performance Initiative, which I believe Ted Huntz will talk about tomorrow, I think. The goal of that is to make 100 megabit TCPs very commonplace. And my point here is that TCP is designed to congest. So if our TCPs really work end-to-end at an optimal level, they will assure that we have congestion points. And this middle motivation here is actually quite critical, and that is that there exist self-policing users today. Particularly in the high-energy physics world, we have folks who really know how to run their TCPs all out. They know how to kill a bottleneck link, and they run at night because it's antisocial to run during the day and kill everyone's interactive web browsing experience or video conferences or whatever. Other things like administrative backups run at night. Scavenger is a tool to be self-policing on a very fine grain. So these folks will be able to run their high-performance TCPs all day long without impacting the best effort network, and in fact have their TCP transaction times reduced by marking them as scavenger. Another motivation is pricing. If you could show that your provider that a certain percentage of your traffic mix is marked for worse service, arguably this could be a potential negotiation point. And lastly, policy. You might very well want to mark, users or institutions might very well want to mark traffic which is non-mission. So the service spec here is a network carries a code point which is defined globally and can degrade it. In the interest of time, I'm not going to go into the subtleties here, but we'd like there to be a small minimum departure rate for scavenger traffic. It's a very nice deployment story. Right now, pretty much every Internet 2 network carries diffserv code points unchanged, and the minimum requirement for scavenger is you just treat the traffic like best effort service, and optionally you degrade it. So arguably, we have a very large scavenger infrastructure today. We recently did a trial of this across an OC3 link from Advanced Network and Services into Abilene. Some iPerf traffic generators there on the hosts, traffic flowing right to left, synced at surveyor machines, OC3 ATM connected surveyor machines in the Abilene POPs. Basically configure a class map to identify the scavenger code point, and we gave that a 1% link share. The interface under test was a frame relay over pause, and here are test results which you can scrutinize offline, but the basic gist of it, the 80 megabits that we got on the case 1 is actually due to a constraint of the ATM interfaces of the surveyor syncs. But you basically see that scavenger and in case 1 and 2, you see that scavenger and best effort both can grab the same amount of the link. In case 3, there's a cumulative throughput of about 135 megabits, which is the capacity of the line, and you can see that you get basically the same throughput here if it's 2 best effort streams as if it's best effort in QBSS. And you see that in case 3, the bandwidth of the scavenger traffic is considerably less than 80. So the summary is that each stream can independently run about 80 megabits with minor loss and small amount of minor jitter and small amount of loss. Best effort is unaffected by turning QBSS on. QBSS absorbs unused best effort capacity, did not make the link any less efficient. We've evangelized scavenger quite heavily in Internet 2, beginning with the March Internet 2 member meeting, and since then we've been watching net flow data through the backbone tracking the success of our evangelizing, and we've seen a rapid increase of scavenger marked traffic. Where is this coming from? Well, 3 university network operators went back from the Internet 2 member meeting and turned it on. Their dorm subnets. So there are 3 university dorm subnets. So it's a small. Those numbers, the scale is pretty small there. We're still well under 1%, well under 0.25%. But that's rapid growth, right? So, but we're working with a number of folks to show some extra value here. There's a project that's quite far along to do a scavenger experiment over the Transpac link to the Grape machine, which is a million n-body simulator in Japan. It generates a lot of data. So there's a lot of big TCPs across that link. We're working both with SLAC and CERN on some HEP experiments on working with the folks who developed the library that sits underneath folding at home and several of the other at-home type applications to make those kinds of CPU scavenging applications also bandwidth scavenging. So in summary, we're continuing with the architecture, the two-bone architecture. It still makes sense. We're tweaking it. We're figuring out how to deploy premium incrementally. In parallel, we're working on much lighter weight things that we hope can offer some value in the short term, namely scavenger. And if you'd like to participate, join the mailing list or join one of our active design teams listed there. More info available here. Thank you. Sorry for running a little over.
Thank you, Ben. So we have a few times for a few questions.
Hi. Do you think that the Firehose model with the mpls scheme that you came up might be not scalable for the service provisioning end-to-end?
I'm sorry, is this a question about
yes,
classification resolution?
You said that you were thinking about having a Firehose where everyone could have his own virtual trunk. Is that correct or not?
So actually, the Firehose model is a single policer at an ingress. So it's in a sense destination unaware, and the virtual trunk is the destination aware model of classification of policing. So are you asking whether doing that destination unaware kind of classification?
No, the destination aware. It could be that this kind of model, although that it's functional, cannot be provided to a very great extent in the network, so that anyone can should signal what is the source, what is the destination, and this should be happen for every ingress and egress node.
Right. So we're very concerned about scalability, but we're also concerned about building an architecture which is fault tolerant, and we're of the belief that this level of classification gives you a considerable amount of aggregation, but still allows you to protect as the operator of one of those single clouds in an interdomain Q-bone infrastructure, allows you to honor your assurances to your peers without being at risk of violating those assurances because of misbehavior by somebody who's not in a business relationship with you. So while at the same time doing that level of classification and having a requirement for that number of policers at the edge kind of limits what actual routers you can use today to implement the architecture, we're pretty sure that you could build a router to do that, and it's not unreasonable to ask for hundreds of shapers. But we can follow up offline.
And last question is, do you think that QPVB, quality QoS policy propagation is a necessary feature for the service?
So you need either you need that level of hook to routing information in your classification in one way or another. You need it either just to police and then let things fly through your network via normal OSPF behavior, or you need that kind of classification sitting at the head end of an mpls tunnel if you're going to set things up that way. So while QPVB is a Cisco-specific thing, I think we need something that does the equivalent, namely at ingress know the next hop AS and be able to take an aggregate, say everything going to this next hop AS will apply to this profile. So yes, I do think it's quite important.
Thank thank you again. I think we have to go to the next talk. This is presented by Emiliano Casalicchio from the University of Roma, and he will describe a concept how the quality of service requirements of web clusters could be managed, could be solved.
Good morning to everybody. I'm very pleased to be here in the Terena Networking Conference, and I'm very pleased to have the opportunity to present to you this preliminary work on mechanism of quality of service in web cluster. In the first section of the talk, I introduce why new web service require quality of service, and how, starting from the well-known principle of quality of service in computer network, we define quality of service in web cluster. In the second section, I present the system architecture that we consider, and I'll introduce the difference between quality of service blind dispatching algorithm and quality of service aware dispatching algorithm. In the last section, I present the simulation results, conclusion, and work in progress. Well, in less than 10 years, we have seen two generations of websites. The first generation of websites provide only web publishing services and some dynamic services like database search. But the new website provide financial, economical, and business-oriented service, and most of the advanced company and organization base their information system on web technology. Then this new web service require differentiation of service and differentiation of user request, support to heterogeneous application and user expectation, and the ability to realize a differentiated pricing for content hosting and service providing. For their complexity, the new web service require high performance before quality of service, and for this motivation we consider the web cluster, that is one of the architecture that permit to realize websites that are able to provide high performance. And our thesis is validated by the fact that most big companies like IBM, Cisco, Foundry Network, Paga realized software product that permits to configure and manage web cluster. Well, but high performance is different from quality of service. This because the quality of service is based on the concept of service level agreement that is a performance contract agreed between the user and the service provider. And depending on the strictness of this contract, a service could be a guaranteed service or a predictive service or a best effort service. We consider predictive service in this work. Quality of service is deeply studied in computer network area, but the quality of service principle and mechanism could not be directly applied to the web because a network system is different from a web cluster system or a web server system. But the next step that is outside the scope of this paper is to integrate network quality of service and server or cluster, web cluster quality of service to realize a peer-to-peer quality of web services. Well, I remind that the scope of the focus of this talk is on quality of web service for web cluster. Well, to define quality of service in a web cluster, we need to find out feasible mechanisms to achieve quality of web service and to find out the web cluster component that can implement this principle and mechanism. Then our idea is to start from well-known principle of quality of service like classification, performance isolation, high resource utilization, and request admission control to define quality of web service principle. Well, in a web cluster, the classification process of client and service and the identification process of user could be carried out by the web switch because the web switch is the component that has the full control of incoming requests. And depending on the type of web switch, of the level of the web switch work, the classification process is different. In fact, in a layer 4 web switch, user may be identified through the IP address, and service may be identified through the port number. And in a layer 7 web switch, user may be identified by a quick information, through a quick information or through some other information in the HTTP header. And service could be classified on the basis of the URL requested by the user. To differentiate the performance of different services, we may use two mechanisms. The first mechanism is queuing scheduling with priority implemented at the main component of the web server, like the CPU. And the second mechanism is the resource partitioning. The components that implement resource partitioning depend on the concept of resource. If we consider as resource the component of the web server, this mechanism will be implemented at the web server. But we think that the best component to realize resource partitioning in a web cluster is the web switch, and then as resource we consider the entire web server. This because it's too cheaper to implement, and because the web switch has the full control of the system and a centralized image of the system load and of the system state. Well, but if we realize a static resource partitioning, some resource could be underutilized, and then to realize a high resource utilization, we need to implement a dynamic resource partitioning, in this case at the web switch. And finally, to prevent a system overload, we need to use an access control mechanism. In fact, for example, if a part of requests reach the website, high priority requests could experiment a performance decrease, and then we must decide to drop the low class request to have an acceptable level of utilization of the system. Okay, this is the architecture that we consider is a web cluster with a layer 4 web switch, enhanced with a mechanism to admit and drop requests, and we suppose that in some cases this mechanism could be implemented even on the web server. Well, usually dispatching strategies that web cluster use are quality of service blind. For example, round robin, distributed server, and weighted round robin. Then this policy could be enhanced with some quality of service mechanism implemented at the web server. For example, an admission control mechanism implemented at the web server, and a priority scheduling of process at the CPU. Then in the performance evaluation, we consider as pure quality of service blind dispatching algorithm the weighted round robin, and we consider even a quality of service blind dispatching algorithm enhanced to quality of service, that is a weighted round robin with a mechanism of access control and priority scheduling at the web server. Quality of service aware dispatching algorithm could be divided into two families. The first is dispatching algorithm without partitioning, and the second is dispatching algorithm with server partitioning. In the first family, we have simple strategies. We consider a simple strategies that implement only an access control mechanism at the web switch, and the same strategies with priority scheduling at the CPU of each web server. And consider a policy that realizes a dynamic server partitioning. In this policy, we divide the set of web server into two subsets, an high set and a low set. The server in the high set are dedicated to high priority requests, when the server in the low set are dedicated to serve all the other requests. The server partitioning is initialized to a value proportional to the percentage of high priority requests that we expect and proportional to the number of servers of the cluster. But a server on the low set could jump to the high set when the cumulative load of the high set is greater than a fixed threshold value. And this web server returns to the low set when the cumulative load of the high set is below another threshold value. I don't want to be tedious, and then the complete description of this formula, this expression is given in the paper that is available on the website of my research group in the next week when I come back in Rome. I don't know if on the Terena website are published the paper or okay. Well, in this table I check which quality of service principles are satisfied by the algorithm. Partition algorithm satisfy all four quality of service principles when all the other three algorithms do not satisfy high resource utilization principle, and only switch admission do not satisfy performance isolation. Well, to evaluate the performance, we build a web cluster simulator with the CSIM library, and we model server with realistic parameter, and we use heavy-tailed distribution to model the workload. And in this case, we consider three classes of services: an high priority services, a medium priority services, and a low priority services. And we suppose that only the low priority request could be dropped. As performance metric, we use the 90 percentile of page delay. The page delay is the completion time of a web page at the web cluster side, when the X percentile is a metric used to define service level agreement for predictive services. And another important metric is the percentage of dropped requests. That is the number of the percentage of users that receive a service denied. Well, in the first set of experiment, we compare the performance of dispatching strategies. The horizontal line is the performance of weighted round robin. The first result is that for the high class of request, all policy realize a response time, a page delay that is less of the page delay provided by the weighted round robin. The second result is the confirmation that switch admission do not realize performance isolation. And policy realizes the best performance isolation. If we look at the percentage of dropped request, partition is the policy that drops the highest percentage of requests, and the switch admission with server priority is the policy that drops the lowest percentage of low-class requests. Well, in the second set of experiments, we consider a variable percentage of high-class requests. That is, we increase the percentage of high-class requests, and we look what's happened. All policy give good results because for high class of request, when the percentage increase, the performance are stable, and these are the price of an increase on page delay for medium class request. And if we look at low class request, we have two behavior depending on the dispatching strategies that we use. Partition strategies permit to realize a stable performance for low class, but in terms of response time, but an increase of dropped requests when the opposite behavior is for the other two dispatching strategies that drop a low percentage of requests, that is less than 5%, but give a response time that increase when the percentage of high-class requests increase. Well, these results are not very exciting, but give us the opportunity to have the confirmation that if we implement and integrate quality of service mechanism in the right resource, in the right component of a web cluster, we may realize a web cluster enabled to the quality of service. But this is a preliminary work, and we now are working on a layer 7 web switch that permit a finite service classification and user identification, and then we are studying policy for dynamic partitioning that we retain is the best quality of service aware dispatching strategies, even if it's the more complex. And in parallel with the simulation, we are implementing a quality of service aware web switch on a cluster of Linux machine. If you have any question.
Thank you, Emiliano. Other questions? Okay, then thank you again.
Thank you very much.
And
sorry? Tell me.
Thank you again, yes.
Okay.
So we go to the next talk. This is presented by Juan Antonio Martinez from the Autonomous University of Barcelona, and he will present a concept to implement quality of service in a campus net environment.
hear me? No. Yeah. Well, I would like to explain some concepts on quality of service evaluation model for a local area network. In our case, it's a campus network, a university network, and it's the work that we have performed. Not only me, that I will be the person who explains it, but with 2 people more at our university. First of all, the talk outline. I would like to first define the objectives that I would like to meet. Then the classical approach to quality of service, because in our opinion, this quality of service model is adequate for one environment, but perhaps for the local environment, it's not as accurate as we would like. Then we would try to find a generic model for every network, mainly based on availability. This would be for the low layers of the network. And then we would like to expand this model also to the services. I will explain which have been the practical results that we have obtained in our university, and then some kind of comparison to other existing products and future work. Finally, a short conclusion about this study. Well, the main objective was to determine if our network reaches the 5 nines model, that is a 99.999% of availability. It has been, or there has been a lot in writing about which is the availability of a network, but we have found nothing that gives this availability for a local environment. In one links or in telephone companies, we can get of the availability, but not for a local environment. We would like to evaluate also the quality of the network, not only for the infrastructure, that it's really important for us, but also to the services that are running in this network. Finally, for the model that we would like to find, it must be quite simple. We don't want any complex solution. And in our campus, it's a network that is continually growing. The model that we find should adapt easily to any kind of topology change. Well, how have we obtained this model? First of all, some ideas on the classical approach to quality of service. Quality of service is evaluated as a combination of delay, jitter, and packet loss. This is quite useful for one links because it's easy to take a number on both router endpoints, and with no special work, one person can know which is the delay between 2 router endpoints, or the jitter, or the packet loss. But for the LAN environment, some complications arise. We can see that the parameters are difficult to determine because nowadays mostly we have switched environments. So this distributed environment, these parameters are different for each segment. So it's quite complicated. Also, we are not sure that the guarded data is significant because the nature of Ethernet traffic, it's bus traffic, and perhaps the values that we get are not quite significant. Well, which are the problems? As I have already said, the quality is not assigned a numeric value. We just compute a set of parameters, and well, we have a number of these parameters, but I don't know with these parameters if the network is really good or not. Also, for the LAN environment, the network probes must be distributed all through the network. If we have a switched environment, I think it's often the case. Each segment provides a different value, and it's a model that it's expensive to implement because we need to distribute this kind of measurement points. Due to the traffic nature, as I have already said, the values are perhaps not really significant. In fact, we can outline that it's not a model with what we have, but just an evaluation of these parameters. With this, which were the basis for our model? First of all, it was a need for us, a model with low cost. Also, the quality of service should be given as a numeric value. and the model should be really flexible to adapt to network topology changes. The initial idea was to get this data from simple tools that could be portable to any network, and this was easy to accomplish with ping, for example, and tools like SNMP queries. We have discarded other approaches based on modified TCP stacks or proprietary ping solutions or any other solutions that need a special configuration that was not standard, let's say. Which is the idea for this development? First of all, we assume that all the network devices have management facilities, and that we also know the number of users that are affected by a network failure. We think that for a network manager or a network administrator, both of these constraints are not difficult to satisfy. The general idea or the algorithm that we would like to follow is to choose the critical network devices. We weight them accordingly. That means that a device that is more critical than another will have a higher weight. With these values, we determine which is the availability at a given time, and then compute the mean value over time. Well, this would be an schematic view of our network. As you can see, it's a central switch who distribute to other switchings all around the white campus. And finally, we have user points, which can be switches or hubs. But we simulated what happened if we considered all the network or just these central devices, and we saw that there was no particular difference, and so we center our study in the two main levels of this switching network. There's no problem if you like to consider all the hubs, routers, switches in your corporative network. These ideas can be mathematically expressed with two important values. First of all, we define a relative availability coefficient. That means that every switch in our network will have a different value. A switch that holds a lot of users would have more importance than another one. Also, we introduce an additional coefficient that tells us if a determined segment is especially important or not. Finally, we need a binary value that tells us if a segment is or not accessible. With this, we can compute the instant availability just as a sum, and for the mean value, if we made a continuous sampling, we should have an integrate that would give us the mean value over time. We don't make a continuous sampling, and so we make only discrete intervals, and we sample at constant intervals. With this, we can make this availability not an interval but a sum. And then, if we make some simplifications, we can see that if the samples are constant, the computing can be evaluated only with the numbers of samples, the previous mean value, and the last samples that we have got. This is quite focused only in infrastructure, but we would like a model that would be also that we could also apply for the services. The first problem, or in fact the first goal, is to determine whether this model we can determine if a service is working or not. We cannot rely on ping solutions because we cannot tell if the mail service is running or not just with pinging. So we think that the model is still valid, but we need to omit these criticity values and determine the instant availability with other tools. This is quite theoretical, and we would like to know some details of the implementation that we have carried out in our university. First of all, and for network availability, as I have said, we choose the ping tool because it's quite extended and it's quite easy, and everyone has access to such a tool. As I have said, we we consider only the second level granularity, although you can consider every device in the network if you like. We have chosen coefficients for every device, and finally, a global coefficient that is computed from these two coefficients, and a configuration file that stores all this data in order that a program can access this data and compute the instant network availability. The configuration file that we have used or that we are running is something like this. In fact, it's this one. We have a mnemonic name, an IP address, and then an availability coefficient. With this one, we have one program that I will tell something about it later, that take these coefficients and is able to compute the instant availability of our network at a given moment. Regarding the services, the model is essentially the same, but we don't have now a ping tool, and also for each machine, we like to know which services are important to monitor. With the system we have developed, we can evaluate proper function of a service at a given time and compute this availability over time. I must say that this part of quality of service is only one part of the global project, because we also use it for monitoring purposes. In this, especially for the monitoring, we have developed a proprietary MIP that we implement in the different servers in order to know critical parameters of something like the time response of a mail server or the disk space or every other parameters. If someone wanted to implement something like this, what would he need to mount it? Well, first of all, a set of C programs, one for each service that you want to monitor. Then a configuration file that holds the network and also the services. And for the services, we hold the host name and the services that are important for us. For example, for our mail relays, we would like to test SMTP, POP, or IMAP functionality. Optionally, this is not mandatory. If you like, you can implement a MIP in order to get more detailed data. Well, some numbers on this implementation in our campus. First of all, for the development, we have made it in a PC with Linux, Red Hat, and a standard compiler, and we have tested also the portability of our software, because we are running it in two machines, a PC with Linux and also a Sun Enterprise. I must say that these machines are not dedicated only for this purpose, because it has no special requirements. We have seen that our networks has achieved monthly values between 98.5% and 10% in some months. For the services, we use for availability, we would like to know the availability values, but we use it mainly to test that all the services are working properly. So what we get, or what we keep, is the availability mainly for the network connections, although we can keep also the services if it's important for us. As a global overview of the system, we have made a set of routines that verify that all the network services, or the services that classically are more associated to network, are working properly. We have made it with BootP, DHCP, DNS, FTP, also the mail, and the news. We can verify any of them. Then we have a program written in C code that implements the mathematical model that I have already described, and the configuration file that stores both the coefficients for the network model and also the services that we want to monitor in each server. Optionally, as I have said, if you like to make detailed monitoring, you can use a modified version of the SNMP daemon in order to retrieve important data. This would be for monitoring, but not, in our case, not for our implementation of the quality model. To get an idea, because when we began to implement this model, we didn't know which kind of values we could get for the network. And I must say that we are not, our network is not 5 nines. In fact, I doubt that any network can be, although many people claim that they do so. We have months that we have 10% availability, but there are other months when we have only slightly upper 98 or 98.5% of availability. Regarding the service monitoring, if you like to do so, we have implemented our own programs, and they are especially useful for the network operators in order to detect network problems. The operating modes of these programs, you can choose to run them interactively or also Chrome-based, and send you can configure them to generate a mail or an SMS message if any problems are detected in the network. For example, for a simple execution, we can get all the services in a configuration file and test whether they are working properly or not. This level of verbosity you can also configure, and it's really interesting for the network center because you have a centralized point, and from there you can choose to monitor all the service around the network. We know that there are other existing products, and in fact we are using some of these products also. And I would like to make some comments on these other products and a little about some open future work on our. I think that there are two big groups of software that have something to do with our programs. We would have the monitoring tools and the graphic or displaying tools. For the monitoring tools, there are tools that are quite powerful, and if you like, I would encourage you to test them, because softwares like Big Brother or NoCool can provide you a lot of information about how are the services on your network. On the other hand, for the graphic tools, they are not monitoring tools. They are just graphic tools, and in some cases, they are easily to integrate with other monitoring tools. This would be the case, for example, of MRTG or other softwares that exist in the market. But in fact, none of these services, none of these programs gives a detailed model of the network, or you cannot configure if for you it's important one segment or another. This was why we decided to implement our own model. As a future work, we would like to make a little more analysis about the integration of multiple distributed meters, because perhaps, in fact, we are running two machines, and sometimes we get different data from the two. We would like to know if what happens, or how can we integrate different meters all around the network. Also, we need to improve the web interface, although in fact we are not hard working on this subject, because there are others, like for example Big Brother, that can do so, and they do very well. Finally, as an interesting line, we would like also to make a web interface to our monitoring system. This is essentially what we have carried out, and let's extract quickly some conclusions. Which are the benefits of this system? First, we have a central point for verifying proper function of all the services around the network. In order for the model, for the network model, it's quite flexible to adapt itself to network topology changes and to add new servers or services. We get monthly reports of both internal and external connectivity, which is quite useful for us because we can tell in our reports which has been the achieved values for every month, and if there's something that fails quite a lot, we can repair it. Finally, we get only availability for services that are really important for us. And in order to make graphic documentation, it's easy to integrate it with other tools like MRTG, which we are currently running also in our university. If you like more information on this system, you can get this presentation either on the Terena web server or in our FTP sites. Also here you have our addresses in both the presentation and the papers. So if you have any questions, you can please feel free to ask me. I think that's it. So if you have any questions.
Thank you, Juan. Are there questions or comments?
This?
Okay. Wait a minute.
Are you looking only at the availability of a service, or are you also looking proactive if a service is going down?
Yes. For the reports that we keep, we use just the availability data because we think that in our network, mainly the response time in normal conditions are not significant. But we also run it at constant samples in order to determine if one service is degrading itself. But in fact, I must say that when we detect that a service has a value that it's not normal, we act, but not based on a rising response time, but on a concrete time at a given moment.
Another question?
My question is a little bit related to the first question. I was just thinking that how often have you run into situations where a service seems to be running normally, but in fact it's not. One example can be, for example, DNS, where someone can make an incorrect value in the zone file and then it refuses to load, but for example 9 of the 10 zone files load correctly. So the server is working, but one DNS zone is not working.
What do you mean exactly, but not working? Can you repeat this example?
So it's something like a situation where it mostly works. How easy is to create all the tests that you can cover all the situations?
Yes. I think we don't deal with this problem, to be frank. We only have the verbosity level, and for example, for the DNS, we can choose to query about particular addresses or domain to verify that they are working. But it can definitely happen that you choose to get a local address and you get it correctly, but other parts are not accessible.
If you include only active network devices, does that mean you leave out things like network segments, which in some cases you might have resilience segments for resilience. You might have multiple segments for resilience, and your model wouldn't detect the loss of any of those.
Yes, in our case, our network is it would be for a switched network where we have no this kind of connectivity, let's say, because we just test that we have connectivity to a place, but you can have if I don't know if that's a question, you can have a degraded link, for example. Is that what you mean? But you have connectivity to that place or not?
Yes, that's one part.
Yeah, if you have if you can reach the endpoint, for us the network is running, because our idea was to determine if we give service to our users. So if we can reach a point, for us this point is working properly. Another thing is a monitoring tool that would tell us that a link is down, and despite it is down, we can have a vulnerability, but we need to repair it.
Okay, no question. Thank you again. Then our session is closed now and lunch is opened.